So far, so we have been discussing about the time domain analysis. So we moved on to the second order systems, where the transfer function of the second order system we have been considering this one. And while discussing about the second order system, we introduced two important variables. One is omega n, which is the natural frequency, and another is xi, which we have defined as the damping ratio or the natural frequency. Okay. So based on this generic second order system, we have computed the poles of this system depending on the value of the xi. So if the most generic form of representing the roots is given by this one, where xi is lying between 0 and 1. So the roots are located at minus xi omega n plus minus j omega n 1 minus xi square, where we know that minus xi omega n is negative, meaning to say that the system is a stable system. Okay, and we have also defined the region in onto the S plane, that if the poles of the second order system, or depending on the poles of the second order system lying in whatever region of the S plane, we classified the response either as the underdamped response, overdamped or critically damped response, or the unstable response. Okay, so we'll carry forward that discussion now to discuss about the performance specification of a given second order response. So if you so these are the different responses what we had seen. One is the overdamped response, the critically damped response, the underdamped, and the undamped. So in the undamped response, it is almost like an oscillator. Okay. Now if we pay close attention to the location of the poles depending on the value of psi, so we see that if the for psi is equal to 0, the poles are located on the purely imaginary axis, due to which the step response of a second order system is is oscillatory with some natural frequency omega n, and we defined it as the undamped response. Now if psi is lying between 0 to 1, we have the pair of complex conjugate poles located onto the left hand side, whose real value is given by minus I omega n, and the imaginary value is given by j omega n 1 minus I square. We define this undamped response. Now for xi is equal to 1, we see that the poles are located on the negative real axis, and these are the repeated poles. So this is the response what we get, and we define as the critically damped response. For xi greater than 1, again we have the only real poles located onto the negative left hand side, and the step response of for psi greater than 1, we get this one, which is the overdamped response. Now the important thing in all these responses is that particularly for psi is equal to 1 and psi greater than 1, we see that it's almost like first order, the response what we had studied for the first order system. The reason is pretty much simple. Now particularly for psi is equal to 1, since we have the repeated poles, so this can be represented as s plus s1 and s plus s2. Okay, for both these xi is equal to 1 and xi greater than 1, because the location of the poles are on the left hand side and they are the real. So these two can be represented as the multiplication of two first order system, and the analysis we can carry out the similar analysis as we have done for the first order system. Okay, for xi is equal to 0, we know that the system, there won't be any damping. So the most generic the most generic behavior is for xi is lying between 0 and 1. Okay, so which we call the underdamped response. So whatever the analysis we would carry out, we would do for the underdamped response, so that the other responses could fit in as well. Okay, now limiting ourselves for studying the response analysis for xi lying between 0 and 1. So these are the different types of responses for some specific second order system, what you are seeing here. So you see that if the value of psi keeps increasing starting from zero point 0.1 to zero point 0.8, then the response of a second order system started becoming almost like a first order system. And you could say the overshoot is also reducing. Right? According to the definition what we have used earlier. Okay, and again if the value of psi started decreasing, then we are moving closer towards the underdamped this undamped response. Okay, so let's see what is the generic way of representing the signal undamped second order response. So in this figure you see the response of some underdamped second order system, on which we can now mark our performance specification to quantify the dynamic behavior of such system. So the first of all is what you see is Cmax. Cmax is the maximum value of an underdamped second order response obtained at Tp, which we call the peak time. And based on the Cmax value, we will compute the overshoot. Okay, now this band what you are seeing here is we have defined the steady state region band, which is plus minus 2% of the C final value. Okay, C final is the steady state value, and around the steady state value uh, plus minus 2% we have defined a band that if the response started settling down within this band, then we say that the system started reaching to the steady state value. Okay, now when the response of this system reaches from 0.1 of the final value to 0.9 times of the final value, and the time it takes to reach from 0.1 to 0.9 of the C final value we define as the rise time, this TR, and this TS is the settling time, that after this time the response of the system do not come out of this band, this band, out of this band. So the first performance specification is the Cmax value, which would help us to compute the maximum overshoot. The time, the peak time at which it reaches to its maximum value. Second is the rise time, the time it takes to reach from 0.1 to 0.9 of the C final value. Ts is the settling time, the time after which the response settle down in this band. And the band we have defined is the plus minus 2% of the C final, and C final is nothing but the steady state value. Okay, so these are the overall specifications that we can extract from the response of a second order system. Okay, so now we could see that depending on the generic formula we had used earlier, how we can compute these responses. Okay, so this is the transfer function we had. Now for a step input, we would have Rs is equal to 1 by s, and I could write my C of s as omega n square divided by s square plus 2 xi omega ns plus omega n square. Okay, and after doing the partial fraction, I would obtain that k1 by s for some constants k1 and for some constant k2 and k3. Okay, now since we are analyzing only for the underdamped response as the most generic behavior of a second order system, we would obtain the C of S. You can compute the values of K1, K2, K3 by yourself as C by S, 1 by S plus, it should be minus. Okay, now after taking the inverse Laplace transform, I could write the C of t as 1 minus 1 upon the root 1 minus I square e to the power minus I omega n t cos of omega n root 1 minus I square t minus some phi. Okay, where phi is given by tan inverse of I over 1 minus I square. Okay, so the response what you have seen earlier is of this expression when you have xi lying between 0 and 1, because we know if xi is become less than 0, then the response would be an unstable response. Okay, it would show negative damping. Okay, so first we can see the peak time, or what we have defined is Tp. So Tp I can found by differentiating this expression and finding the first zero crossing after t is equal to 0. Okay, so this we will do this in the frequency domain by using the property of the Laplace transform. That is to say that the Laplace transform of the derivative of the time domain response is basically equal to S of Cs. So here we have assumed the zero initial condition. So S of Cs would yield omega n square plus 2 xi omega ns. Okay, on completing the squares in the denominator, we would obtain omega n under root 1 minus I square, the root 1 minus I square. Okay, now finally I could I could write by taking the Laplace inverse as c dot of t omega n under root 1 minus I square power minus I omega n t sine of omega n under root 1 minus I square t. Okay, now we want this derivative to be 0. The idea behind having this derivative equal to 0 because we know that the tangent or the slope of the tangent at this point would be 0. Okay, so putting c dot equal to 0, we would obtain that it would be 0 whenever we had omega n under root 1 minus xi square t is equal to n pi, and from here we get our tp as n pi omega n under root 1 minus xi square. Okay, now n, by putting n is equal to 1, we will get our tp because we are looking for the first time it reaches to the maximum value. Since in the response, let's see the generic response of the xi lying between 0 and 1, there are many points at which the tangent would be 0. So this would be the first peak, the second peak, third peak, fourth peak. So for different values of n, you would obtain the different peaks. And since we are interested only for the first peak, that's why we use n is equal to 1. Okay, so from there we will get Tp is equal to pi upon omega n under root 1 minus psi square. Okay, so this is the peak time. Now overshoot, we see the overshoot is given by percentage overshoot is C max minus C final, which is the steady state value, divided by C final times 100. Okay, so we can after computing the peak time, you can compute the C max by putting the value of T is equal to Tp, that is C max is nothing but C of Tp if you put T is equal to Tp in your generic expression. And the value we have obtained as C max is equal to C of Tp. After simplifying, you can see that it that it would be equal to 1 plus e to the power minus xi pi divided by under root 1 minus I square. Okay, and since we are considering the unit step input, so in that case we would have C final equal to 1. So the percentage overshoot is now given as e to the power minus xi pi under root 1 minus I square times 100. Okay, so notice one point here, that irrespective of that unlike to the peak time, the maximum overshoot is only a function of xi, not the omega n. Right? So we'll see the 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 effects of xi and omega n onto the performance specifications parameter of the second order system. Okay, so the next performance specification is the settling time. So settling time, we know that the response should stay within the plus minus 2% of the steady state value C final. Now taking the definition, we could write that the response e to the power minus xi omega nt 1 minus xi square under root should be 0.02. Again, this is a very conservative estimate because here we have assumed that the cos of omega n under root 1 minus xi square t minus phi is equal to 1 at the settling time. So in that case, the settling time is basically given by minus ln 0.02 under root 1 minus xi square divided by xi omega n. So this is a bit complex expression, so you would verify by yourself also that once you increase xi between 0 to 0.9, you would notice that this numerator part varies from 3.91 to 4.74. Okay, so the range of this one is quite small, so we could approximate the settling time as 4 upon xi omega n. Okay, so this is the final expression for the settling time. Okay, and this has been also explained in the lecture notes as well. So here we have computed the Tmax or the peak time, pi upon omega n under root 1 minus I square. The maximum overshoot, similarly the percentage. The settling time. So there are some couple of observations from here that for xi less than 0.69, we see that the settling time is inversely proportional to the damping ratio and also inversely proportional to the natural frequency. For xi greater than 0.69, you would notice that the settling time is now directly proportional to the damping ratio, but still inversely proportional to the natural frequency. So depending on the range of xi, the settling time is basically either could be directly proportional to xi or inversely proportional to xi. Okay. So I think we could stop here today because from the next time I will discuss with the steady state errors for the second order system, because the other specifications we had seen how you can compute and extract from the generic second order response. So if you have any queries or doubts, I can take them now, either regarding this topic or some tutorial problems. So there are some extra tutorial problems uploaded on the Moodle. and a submission link is also created, so you can submit your assignment and the solutions there also for me to take a look at them.